Hi everyone, my name is Neha Kartam, and in this lecture we're going to learn about logic gates. So let's begin with the preview of the lecture. So these are the topics which we are going to cover in this lecture. We're going to cover different types of logic gates, as you can see here: AND, OR, inverter, NAND, NOR, XOR, XNOR, NAND gates, and then further gates with more than 2 inputs using inverters to convert gates, and then TTL and CMOS logic gates, troubleshooting gate circuits, and then IEEE logic symbols. Now let's start with the AND gate. So before I discuss the AND gate, we need to know what the Boolean algebra is. So the Boolean algebra is the branch of mathematics which describes the relationship between the inputs and outputs of a digital circuits, where these inputs and output values are called Boolean variables, and the function is called your Boolean expression. So you see here, this is called your Boolean expression, or another name for this is logic function or Boolean function. So all operations in Boolean algebra, they can be created from 3 basic logic functions: AND gate, OR gate, and NOT gate. So we're going to begin with 3 basic logic gates, and then we can make other logic gates which are derived from these basic logic gates, and they are called your NAND gate, NOR gate, and so on. So let's see AND gate. So this is the Boolean expression for AND gate. A and B, these two are the inputs to the AND gate. This is the symbol for the AND gate, and Y is the output. As you can see, the output is coming out from here, and these are the inputs. So now in the next slide we're going to see the truth table for AND gate. So here on the right hand side you see the truth table for AND gate. I hope you remember that the input A and B, when they are multiplied, then the output is produced. So here we have these inputs which are going into A and B. So let's go step by step. In the first case, when A and B, they both are 0, then the multiplication of A and B is going to be 0. So that's why we have output as 0. If B is 0, A is 1, then again the multiplication of these two makes up 0. So that's why we have Y is equals to 0. And then the same for here, when B is 1, A is 0, then again we are going to have Y is equals to 0. The output will be high only if both the inputs, they are high, which means when you're providing 1 1 to A and B, then only your output is going to be 1. So you can also say that all inputs high make output high, and if any one of the input is low, the output will be low, otherwise it is going to be high. Now let's see next. So we have a short test here. It says, what is the output of the AND gate? So let's see. So when you have low low, then output is going to be low. When you have low and high, low is your 0, high is your 1, then the multiplication of 0 and 1 is again 0. So 0 is your low. So you have this. If both the inputs are high, which means 1 1, then the multiplication of 1 1 is 1. And that 1 at the output means high. So you have high here, and then when high low, again the 1 and 0 multiplied will produce 0, and 0 is low. So this circuit you see here is basically showing the truth table which we discussed in the previous slide. And here it says output will be high only when all the inputs are high. So which is true for the AND gate. Now next we have OR gate, and OR gate is also a basic logic gate, and the Boolean expression for OR gate is equals to is a plus b equals to y, where a and b, these two are the inputs and y is the output. And you can see here this is the symbol for OR gate, and you can compare the symbol of the OR gate with the AND gate, and you will see that how in AND gate you have like a straight line over here, whereas in OR gate you have a curved line here. So this is a unique symbol for OR gate, and these two you see are the inputs going into the OR gate, and this is the output sticking out from the OR gate, which is y, and a and b are the inputs. Now let's see the truth table for the OR gate. So different inputs are given here for a and b. Let's start with first this, when both the inputs are low, which means both the inputs are 0. So if you add these by the formula for AND gate is, for OR gate is a plus b is equals to y. So if you add this, this is definitely going to be 0. So you have y as 0. And if you give b as 0, a as 1, and you add them up, you will have 1. Similarly here, you have b as 1 and a as 0. If you add them up, you will have 1. And in the last one, you have b and a. They both are high, which means 1. So if you add them up, then what will be the decimal? It's going to be 2. And if you represent 2 in binary, then you will say 1 0. 1 0 represents your 2 in binary. So here we are just going to use the carry, which is 1 here, and 0 is the sum, so which we will not use. So that's why you have just 1 here. So we are going to learn about the addition, subtraction in binary later on in the coming videos. Right now, for now, just understand when you have two inputs going into the OR gate which are high, then your output is going to be high. So if you see this truth table, you'll get to know if either of the input is high or both the inputs are high, then the output is going to be high. Or in other words, we can say if both the inputs are low, the output is going to be low. Otherwise, it's going to be high. Now let's do a quick test. So what is the output of the OR gate? When two inputs are high, which means we are going to have the high output, because we know that if both the inputs are low, then only the output is going to be low. Otherwise, it is going to be high. So the answer is high. High and low, again, these two inputs will be added. High is 1, low is 0, so it's going to give 1, which means high, and then low, which means 0 0, so addition of 0 0 is 0, which means low. And if low and high, then it will give high. So this is your actually the truth table, and it says output will be low only when all the inputs are low, which is true for OR gate. Now next is the inverter, or the other name of this type of logic gate is called your NOT gate. And so NOT circuit, it gives the output that is not the same as the input. So you see this symbol over here. This is the symbol for inverter, or you can say the NOT gate. You see there is a NOT here. Because of this, this type of symbol is for the NOT gate, and this represents the NOT. So as it says, gives output that is not the same as the input. So if you give A, then you are not going to get the same output here. It's going to be inverted. If you see at the input, we are not doing any addition or multiplication, but still we are getting the different output here, and that is due to this NOT. So whenever you have this NOT, the output, your input will be inverted, and that's what you get at the output. So Boolean expression for the NOT gate is y is equals to a bar. So this is for bar. Sometimes it is also called a complement. So a complement, and this is another way of representation of complement. Y is equals to A complement. So you can use either of ways of writing, it doesn't matter. Now let's see what will happen if we give A is equals to 1. So if we give A is equals to 1 here, then the output, we know it is going to be inverted by this Boolean expression. So what is the inverted value of 1? It's going to be 0. So if you give 1, then the output is going to be 0, and if you give 0, then the output is going to be 1. So this is actually your complement is going from 1 to 0 and 0 to 1. And here you have double inverting. So if you have like double inverting, or you can say double complement or twice complement, then you're going to get the same thing. So with one complement, the value is inverted, and if the double complement, the value goes back to what it was previously. So for example, if A is equals to 1, then the output is going to be 0, because here it is getting one complement. And if you have like another inverter here, so here is your A complement which you got here, and if you have like another inverter, then the output of the another inverter, you will get A double bar, which means it is equals to A. So you are going to get the same input which you have sent here. So with two NOT gates, you are going to get the same input. With one single NOT gate, you are going to get the complemented output of the input. So we got this thing that when you have the double complement, you get the same thing. Now next is the NAND gate, and this NAND gate is basically derived from the NOT and the AND gate, or inverted AND function. And the Boolean expression for this one is A dot B. You know that this is the expression for AND gate, and since we are also using NOT, so for NOT we are adding the complement here. So for NAND gate is A dot B complement is equals to Y, or you can use this representation which is A dot B, and then you have a dash here is equals to Y, and this dash represents your complement function. And this is the symbol for the NAND gate, and if you compare with the AND gate, then you will notice that you have a NOT here. So this NOT represents your NOT gate, and this is your AND gate, so which makes it as a NAND gate. Now we're going to see how the truth table looks like for the NAND gate. So similarly, we are going to give the input to A and B. So these are the 4 different combinations we can give to A and B, which are 2 inputs going into the NAND gate. So now we are going to have, so what we are going to do first, how to find Y. Y is equals to A dot B complement. So the first thing we can do, let's just first write down what are the outputs when we just use the AND gate, and then we can just complement it. So that's we have done here. So we have put the value of AND gate, the output of the AND gate here. And you know that in AND gate, if both the inputs are high, then only the output is high, otherwise it's going to be low. So that's what we have put here. And now we can complement these outputs, and whatever the complement values we will get, that will be our main output for the NAND gate. So you see here, this is the AND. The first output is from the AND gate is 0. So complement of that is 1, and same with this 1, same with this 0 to 1, and this was 1, so now it's going to be 0. So this output you see is basically representing your Y, and this is the NAND output. So if we see, look at this output, we can say in case of NAND gate, if both the inputs are high, then the output is going to be low, otherwise it is going to be high. Now let's do a quick test. So what is the output of the NAND gate when they both are low? So easy way to the calculation is like in the AND gate we multiply, so we will multiply 0, 0 is going to make 0, but then we have a complement here, so the output 0 is going to turn into 1, which means high. So we have high here, and then we have low and high here. So if you multiply, it's going to give a low, and then the complement of low is high, so we have high here. And similarly, high, high, 1, 1, so multiplication of 1, 1 is 1, which is high, and complement of 1 is 0, so that's why we have low here. And this case is similar to this case, so output is going to be high. So the output will be low only when all the inputs are high, and this condition is true for the NAND gate. Now the next gate is NOR gate, and NOR gate is derived from NOT gate and OR gate, or you can say inverted OR gate, and this is the Boolean expression for NOR gate. I hope you remember, for OR gate we use this expression where A plus B is equals to Y. So in the NOR gate we are going to just add the complement here, so this complement represents your NOT gate. And this is another way of representing it, A plus B and whole bracket and a dash. Dash represents your complement, which is equal to Y. And this is the symbol for NOR gate. So this is your OR gate, and then when you have a NOT here, that will make the gate as a NOR gate. Now let's see the truth table. So for NOR gate, we are going to apply the same method which we applied in the AND gate. These are the different combination of inputs, and this is the output which we get from the OR gate, and then we will going to take the complement of these output, and whatever we'll get is the NOR gate. So you know that in OR gate, if both the inputs are low, then only the output is going to be low, otherwise it is going to be high. So this was our output from the OR gate, and when we take the complement of the OR gate, which will make NOR gate, then we will have for this case we will have 0 to 1, and then for all next 3 cases it's going to be 0. So in summary, we can say that in NOR gate the output will be high if both the inputs are low, otherwise the output is going to be low. Now let's do a quick test again. What will happen if both the inputs are low? So if both the inputs are low, which means 0, 0, the output is going to be 0 for OR gate, and if we take the complement of 0, then it's going to be 1, which is high. And then we have low and high, which is 0 and 1, and adding them up will make 1 for OR gate, and then complement of that is going to be 0, so that's why we have the low output low. And then this is going to be same again, because this is the similar case, high 1 and 0, adding them up will produce 1, and then complement of 1 is 0. And when both the inputs are both the inputs are high, then the output is going to be 1, and complement of 1 is 0, so output is going to be low. So the output will be high when all the inputs are low, so which is true for the NAND gate. Now next gate is XOR gate, and this gate is also known as exclusive OR gate. We can also say that anything but not all gate. So the Boolean expression for this type of gate is A, and then you have a symbol like this, and B is equals to Y. So which means A XOR B is equals to Y, and here is the symbol for XOR gate. You can see this shows a OR gate, and then if you have something like this, then that makes up a XOR gate. Now next we are going to see the truth table for the XOR gate. So here you have the same B and A. These are the inputs, and these are the four combinations we have. And then you have the OR gate and the XOR gate. So for the OR gate, the output is going to be low when both the inputs are low, otherwise it's going to be high. So this thing we have already seen. XOR gate, which is the exclusive OR gate, is a special case of the OR function, and in this case the output of the two input XOR gate is going to be high when one and only one of the input is high. Then only it is going to be high. So this is the XOR gate, and this is the output Y for the two inputs. If these two inputs are going into the XOR gate, then you will have output like this for different combination of inputs. Now let's do a quick test for XOR gate. So first we have all low, which means all 0. So in this case the output is going to be low for XOR gate, because we need at least one of the inputs should be high. So we have low here. Second case, one of the input is high and other of the two inputs are low. So our output is going to be high in this case. Third case, when all the inputs are high. So when you have all the inputs are same, then output is going to be low. So that's why we have low. Now in this case we have at least two of the inputs are high and other inputs, the third input is low. So in this case we will going to have the high output. So we can say that XOR output is high only when odd numbers of inputs are high. Now next we have the XNOR gate. XNOR gate stands for exclusive NOR gate, and it is the inversion, or you can say inverted of XOR gate. So we remember this is the expression for XOR gate: A XOR B is equals to Y. With the addition of the complement, it will make up the inverted XOR gate or exclusive XOR gate, and this is the another way to represent that. And so here you can see the NOT is added to the XOR gate, which has made this logic gate as XNOR. Now let's see the truth table. So in the truth table you see here XOR gate output, which means if any one of the input is high, the output is going to be high, and XNOR is going to be the complement of the XOR gate. So so this 0 will become 1 and these two ones will become zeros. This 0 is going to become 1. They are all complemented. So we can say that if both the inputs are same, then output is going to be high, otherwise it is going to be 0. So now let's do a quick test. If all the three inputs are low, so by the by XNOR gate we know that the output of the XNOR gate is high when the inputs are the same and low when they are different. So here inputs are same, so output is going to be high, and here inputs are different, so output is going to be low. So inputs are different, again output is going to be low. Inputs are same, so output is going to be high. So the XNOR output is high only when odd numbers of inputs are low. So next is the NAND as a universal gate. The universal gate, it can be used in combination to create any other logic functions, and NAND is your universal gate. So for example, you see these NAND gates are used in this particular example. So you can see that A is the input going in here, and that's the same is input going in here. So the NOT of that is going to be A complement, and same is here is going to be the B complement. So the A complement plus B complement, and then this NOT will make one more complement. So if that happens, then you're going to get A plus B. So which means that with the help of NAND gate, you have made a OR gate, because this function which you are getting at the output, y is equals to A plus B, is the OR gate. So this, with the help of NAND gate, you can create the OR gate. Now, using inverters to convert gates. So here you can see two inverters are used as inputs, and they have been added to the OR gate. And if we have something like this arrangement, then that will make up our NAND gate. So you can try it out. So for example, connect this NOT to the one of the input, and connect the another NOT gate to another input of the OR gate. So for example, if you have A here going in, then the output is going to be A bar, and if you have B here, then the output is going to be B bar. So which means A bar is going into the OR gate and B bar is going into the OR gate. So the output is going to be A bar plus B bar. So, and that is basically the output of the NAND gate, A bar plus B bar. So you can see that how using the inverters we can convert it into a different gates. So this was the example. Now next we have practical logic gates. So the practical logic gates, they are made up of ICs, and in the ICs there are different logic gates which are present. We'll be using some of the ICs in our laboratory experiments to test it out, how the logic gates works. And then TTL families of ICs which are very popular, and CMOS, these are used, families of ICs which are mainly used in for logic gates. So the practical logic gates, if you see, they will be made up of mostly these two ICs, TTL ICs and the CMOS ICs. Now, troubleshooting simple gate circuits. So the first thing is logic probe. Equipment used to test the circuit is very important when you are troubleshooting the simple gate circuit. You need to see how the IC is, how the temperature of the IC, whether it is hot or cold. If it is hot, then you might need to replace the IC because it might be damaged. Look for broken connections, signs for excessive heat, smell for overheating. So this has happened multiple times with the students when they work with ICs. Then when they make the wrong connections, then a sudden overheating takes place, and they can basically feel that through the smell. So if something that happens, then which means something wrong with the circuit, and most probably in that situation the IC goes bad. Check the power sources, which is very important when you build the circuit. Make sure that power sources are connected correctly, the polarity is connected correctly, and then trace the path for logic through circuits. And then once you have built the circuit, make sure what you're trying to achieve from the logic gates, you are getting the same thing. So for that you have to follow how the logic is going, because sometimes the circuit may get complicated, and with small mistake you can get like a totally different output. So it's important that you go step-by-step approach and see what you're getting the output for each logic gate. Now next is IEEE logic symbols. So the IEEE logic symbols for different gates, it is different than you will see from the traditional the logic gates which can be seen in the books. So we're going to see how it looks like so that you don't get confused if you see that symbol. So here you can see this is the symbol for the AND gate according to the IEEE. So you should be familiar with this type of symbol just to make sure that you knows everything, but we are going to follow the convention which I have told you in the previous slides. That is normally being followed, but it's good to know IEEE follows this symbol. For AND gate, these are the two inputs, and this is for AND, and then Y is the output. So this is your AND gate, and then you have OR gate. OR gate looks like this. These are the two inputs and this square box, and then this is the Y is the output. So this is all about logic gates, and this is the end of the lecture. Thank you so much for watching.